We want to talk about the maximum range now. Note, I would never, I want to warn you about this equation. It's one of the most misused equations in projectile motion. Okay. And it goes something like this. And I think it's worth going through this a couple of ways, because I think there's some physics here that we talked about a little bit once. And I want to revisit that so that you could see that there's multiple ways of solving a problem. So here's what we find here. If you take a shot of an object, let's say that you're shooting this from ground level. And what we're going to do here is that I'm going to shoot this with some initial velocity. So that means I have initial speed, and I know that I have an angle involved here. What the projectile motion is going to do here is that it's going to go something like this. And what's really important here is that as this thing is moving, what you're seeing here is that, look at the height. Look at this height. Look at this height. That the launching / landing heights are, let me get this, are the same. And that's one of the most important pieces here. Okay? That's a super, super, super important piece. Because if you don't do this with the range equation, if you don't realize this, this equation will immediately cause problems in your calculations. So what I want to do here is that I want to derive the maximum range equation using two methods. So let's go look at method one. And the way you calculate maximum range, this is probably the most common way. So we know that the time to reach maximum height for a symmetric trajectory should be half the total time. In other words, the time to reach maximum height is half the total flight time. Now, does that make sense? Well, we know we're in the situation of free fall, right? If we're in a situation of free fall, what we know about this situation is that you could imagine that I have a scenario here where this is the ground right here. And what I know here is that when an object is launched from right here, if it's launched, I'm going to launch this guy up with some initial velocity in the y direction. And then what it's going to do here is it's going to keep coming up here, and then it reaches a point of maximum height. And then what happens? The ball turns around vertically, and then the ball is going to come all the way back down. And then right before it hits the ground, it's going to have a velocity that's negative. The final velocity is going to be the negative of the initial velocity that it is. And what we said here is that if I have a symmetric trajectory, we know that the time up should be equal to the time down, which then tells us that the total time should be twice the time up or twice the time down. So we only need half of that. Okay, so that's what we meant by a symmetric trajectory and it taking half. So only v initial y determines the time in air. So the initial y component tells us how much time the object is in the air. So when I set up my table and I start to look at how do I calculate my time, right? If I don't know what the maximum height is, but if I want to figure out what my time is here, right? This guy tells me that it reaches max height. That's why I said Vy equal to 0 up here. Maybe I should have written this up here, but I didn't. Vy at maximum height is 0 here. And so when you look at this thing here, you could see here is that if I go calculate time, it's this equation that's going to tell me what to do. And it tells me that I'm going to get Vy equals V initial y plus AY t. So I'm going to make that black. Right? I know that's the case, but this is the time to get all the way up to the top. So when I go and I look at this thing here, I know that this guy is 0 at the top. So therefore, the time to get up to the top is then going to be minus V initial y over AY. And when I plug in everything here, it's going to be what? It's going to be the initial sine of theta divided by g. And this is the time to get all the way up. But if I know the time to go up, I know the total flight time. So then what this tells me here is that the total flight time is twice that to get up. So what you're seeing here is that I'm getting 2v initial sine of theta divided by g. So I now know the total time in this scenario. So by knowing one, I really know what the other one is here. So if I want the maximum horizontal distance, then what I can do here, let me move this up here a little bit. To get the maximum range equation, we know that the maximum range is then going to be when it has maximum time. And so what you're seeing here is it's got to be V initial x times the total time. But we know that this must be V initial cosine of theta times the total time divided by g. And so this relationship then reads, of course, 2 V naught squared cosine theta sine theta divided by g. And this is what's known as the range equation, as they write it this way. And that's a very, very handy relationship to have, but also extremely dangerous. What I want to do here is that I want to derive the total time using two ways of doing this. And I still want to come back to this relationship, but before I get away from, let this get away from me, I want to show you that there's another way of thinking about this, okay? And this is what I call method 2. And this method could be quite powerful when you're solving problems. Now, one of the things, if we're thinking about the range equation, is we're thinking about the following thing here. what we know here is that the launch and landing heights are the same. Now, if that's the case, then that means that the height change is 0, right? It's 0. So when I'm looking at my trajectory here, right, if this is my trajectory here, and I'm looking at this object as it's coming in, what we're seeing here is that it has to be like this. So the final and initial heights must be the same. So therefore, the height change has to be 0. Another thing that's really important that I said earlier is that the speed at which the object goes up must also be the speed at which it lands. The difference is that this is positive because we define that as positive, and this guy for the velocity is negative, so this has a negative value. So we know what the final speed of the object is. So with this scenario here, we know that the final speed or final velocity is then going to be Vy. So in this case, it's got to be minus V initial y. So look what happens if we think about it in this language here, right? We didn't think about a trajectory. All we did was think about this in terms of where does it start? Where does it end here? So now if I come back into my OneNote here, what I want to show you here is that if I set up a table, that is 0. And of course, my AY is minus G, but now VY has to be minus V initial Y. My initial Y, of course, is V initial Y. And now this thing represents the total time in the air, right? So what I can do here is that I'm going to take advantage of that 0 here. So I'm going to use this equation where I take advantage of that 0. And the equation to really do this with is there's only one, is delta y v initial y t plus 1/2 a y t squared. So look what happens here. If I play with this, note that this is 0, v initial y t, and then this will be 1/2 minus g t squared. That 0 simplifies the equation. And what you're seeing here is that, note, this 2 tells you that you have a quadratic. But wait a minute, what does a quadratic equation really tells you? It tells you that you have what? This implies here that you have 2 possible solutions. So with this one, you can actually see these 2 solutions if you factor out a t. And what you're finding here is that you get v initial y minus 1/2 g t times t. And what you're seeing here, believe it or not, is that there are 2 t values right here. I'm going to call this one t1. I'm going to call that one t2. I don't have to do that. So the question, when you're looking at this equation, what it's really telling you is that the 2 possible solutions is when the object is at y equal to 0. So you could see here is that if I look at this thing here, one solution to this equation is t equal to 0. But at t equal to 0, that means this is at the initial position of the projectile. So of course at t equal to 0, it's at 0. It's got to start someplace. So then T2, what this does here is it tells us the next time the projectile is at 0. So the only way we can do that is that we have to take the parentheses term and solve that for T2. So if you do this, you're going to find here that T2 is really the total time. And if you compute this value, guess what you get? If you do the algebra, you get 2 V naught sine of theta divided by G, which is the total time. And look at this time and compare it to that time. It's identical. There's 2 ways to solve this problem here. So we have the maximum range equation now. So what I want to do here is that I want to interpret the range equation. Okay, I want to interpret the range equation. So the first thing that we want to do here is we say that the maximum horizontal distance, which is r, is then equal to 2 V naught squared cosine theta sine theta divided by G. And one of the things that we said here is that this is only valid if the launch and landing heights are the same. So let's make sure that we get this picture down so that hopefully nobody uses it incorrectly. So when I'm looking at this guy, what this means here is that this guy, because we have same heights, this means we can use it. So it's okay to use range equation. But what about this scenario here? Suppose you have something that goes like this now. And so now what I'm having here is that the ball starts here and the ball ends here. So then as the ball is taking this path here, you could see that these 2 heights, they're not the same. So that means when you look at the range equation, if you try to use the range equation in here, it's not a valid statement. You need both heights to be the same. So now let's go and look at where I want to go with this. So the piece that I want to look at here is that when do you get maximum horizontal distance here? So what you're finding here is that the first thing that I want to look at here is that at what angle does the projectile get maximum distance? And the only way to answer this question here is that you got to use calculus. So the way you do this here is that, so you got to take the derivative of r with respect to theta. In other words, if I look at r, and I take the derivative with respect to theta, then I'm really taking the derivative of this guy, of this expression here. Divided by g. Now, and then what you do here is that you got to get the critical point, which then I set that equal to 0. So the first thing that you want to note here is that note that this guy and this guy is constant, so I can just divide that out. So what you really got to do here is you got to take the derivative of cosine of theta times sine of theta with respect to theta here and set that equal to 0. When you solve for this critical point, what you find here is that you get theta is 45 degrees. So at theta equal to 45 degrees for objects that are in projectile motion, then this gives you the maximum range. Now with air resistance, it changes. Air resistance, it turns out that depending on the air density and stuff like that, but it's about an angle of 52 degrees here. Now, so what does that mean here? So if you think about this thing physically, what's special about 45 degrees? And what's special about 45 degrees here is that when you're looking at components, so from a component viewpoint, "45 degrees essentially maximizes both components." It's like the sweet spot, because at 45 degrees, what you're seeing here is that the length of the y component is balanced out by the length of the x component. They're equal. In other words, v initial x and v initial y, they have the same length. And so when you're looking at that speed, that's the speed that you're going to not only, what you're going to do here is that in this case here, you're going to maximize sort of like distance. And then this other one here is maximizing time simultaneously. And physically, that's what that 45 degrees means. That when I have that angle of 45, I'm really hitting that sweet spot. So now look what happens. If I go a little bit too high above this, right? So now if you're above this thing here, so now if v initial y is a little bit bigger than v initial x, then you're spending how do I say it? You're spending more going vertical than horizontal. But if v initial x is greater than v initial y, even by just a little bit here, what you're doing here is that you're spending less time in air, which reduces, horizontal distance. So it's really a combination of hitting that sweet spot, if you can say that. So what I want to do here is that I want to show you something that's really bizarre about this thing. And what I would say here is that, I mean, there's a remarkable fact about cosine times sine. Is a remarkable fact about cosine theta times sine of theta. And let me show you what it means mathematically here. So imagine that we look at the angle 30 degrees. And then I look at the angle sine of 30 degrees. So this guy's going to be the square root of 3 divided by 2. And this guy's going to be 1/2. So when I multiply these two together, what you're going to get here is that you're going to get the square root of 3 over 4. This is what's remarkable. If you have cosine of 60 and sine of 60, then the cosine and sine reverse. In other words, this becomes 1/2, this becomes the square root of 3 divided by 2. And so when I multiply these two together, I get the exact same value. So I get the exact same value when I do that. And what the observation is that you're finding here is that the sum of these two angles is 90 degrees. So any combination that sums to 90, so if I generalize this thing, it says this: any combination that sums to 90 will always give you the same number. In other words, I could do 20 degrees and 70 degrees, or I could do 40 degrees and 50 degrees. As long as I have that combination, I'm always going to get that. So what I want to show you here is, let's go look at the applet. Okay, so let me go share my screen with you so you could see what I'm looking at. And let me make this a little bit smaller. And so what you're seeing here, let me adjust this. So what I want to do here is that I want to take two shots. So let's start at 30 and 60. So I'm assuming that you're seeing my screen right now. So what I've done here is that I thought I set this to 30, but it's saying 45. So I'm at 30 degrees now. Right, let me make sure that I reset this. So I'm at 30 degrees. And I'm shooting this at 10 meters. So now check out this shot here. So if I shoot this, you could see that the range that they're telling me looks to be just under 9 meters. Okay, looks to be just under 9 meters. Look what happens when I shoot this thing. Okay, so the distance that it traveled here is 8.83. But now if I'm going to reset this thing here, and I'm going to put 60 here now. Look at the distance. Even though it goes higher because it has a bigger y component, when I shoot this thing, you could see it goes to the exact same height. And I can do the exact same thing with, let's say, 20. Right? I thought I'm typing in 20. Maybe I have to reset this. So if I come over here, I'm going to put 20 in here. Not 210, but 20. And if I reset this and then I shoot this, you could see here is that 6.65 horizontal distance. Now, if I I'm going to come in here and I'm going to put 70. So 70, what, 6.55. Let me reset this to 70 now. And look at that, 6.55. So even though it goes higher, it still lands in the same location. And I think that's a remarkable relationship of the range equation, right? Because the reason why that's remarkable is the range equation essentially says that it's 2v initial cosine of theta times sine of theta divided by g. You're going to get the same range no matter what here. I don't know. I think that's a pretty awesome thing that you can actually imagine here.